So in this video, we shall attempt to factorize any m by n matrix A with the use of a diagonal matrix, like we did that for symmetric matrices before. Let's write P inverse. So we want to write this kind of factorization with a diagonal matrix for any matrix A. So our idea would be that we shall construct a matrix ATA and or the transpose of A times A, and you can see this will be a square matrix as well as it will be a symmetric matrix. Okay, and you saw in our study that the eigenvalues of this matrix are all non-negative. Okay, so that is what we are going to take help from in constructing this diagonal in the way we are going to proceed now. So let us look at this 2 by 3 matrix that we are going to try to diagonalize. Alright, so what we shall do is first we shall write the transpose. And what is the transpose? The rows just turn to the columns, right? And then we are going to create a symmetric matrix by multiplying A with its transpose, and doesn't matter whether you let me not go further on this to distract you. Let's look at this here. That is ATA, and if you look at the product is this, and this is a symmetric matrix, as you can see. And now we are going to find the eigenvalues of this symmetric matrix, and this one, in this case of this type, all the eigenvalues will be non-negative. Okay, so let's find the eigenvalues as well as the eigenvectors of this matrix. Now, to save time, what I'm going to do is that I'm going to skip the procedure of calculating the eigenvalues and some eigenvectors corresponding to those eigenvalues. Okay, so here are the eigenvalues 16, 6, and 0, and I wrote them in decreasing order. And here is an eigenvector corresponding to 16, another eigenvector corresponding to 6, and an eigenvector corresponding to 0. And now remember the terminology that the square roots of these eigenvalues, they are called the singular values of the matrix that we were originally given. And so these are the singular values here, 4 and a square root of 6. And these non-zero singular values will give us the diagonal type of, not necessarily a diagonal matrix, okay, matrix when we go ahead and factorize it. All right, so let's look at this square root of 16 and square root of 6. And the way we are going to write our factorization is this. So again, recall that our matrix A is 1, negative 1, 3, 3, 1, 1, and ATA has eigenvalues. What they were 16, 6, and 0, and the square root of 16 and that of 6 and of course that of 0 are singular values of this matrix, that is our original matrix. So what we will do is that we shall attempt to factorize A like this, that we will have a matrix U with an orthogonal matrix, and a matrix D, a diagonal type, as I said. And let's just write the way your book writes. That is the book by David Lay et al. All right, where it's a transpose of another orthogonal matrix V. All right, and this thing D will be of the type made up with these, that is see, square root of 16 is 4, that of 6, let's just write that as 6. So we will have 4, 0, 0, square root of 6, and then in the remaining places we have zeros. So this is our matrix D, and now we are going to construct our matrix V. And remember what we call V as, if you remember from your readings, that the column of V, they are called the right singular vectors of the matrix A. Now, a way to obtain these right singular vectors is this. So you will write the eigenvalues of this ATA in decreasing order, and write the eigenvectors, or write some eigenvectors of these. Like here is an eigenvector of 16, and that of 6, and that of 0. And then we will go ahead and normalize them, and they're already orthogonal, as you can see. So let me erase this portion, and if you go ahead and say try to normalize them or create vectors of length 1. So what I'm doing is I'm simply dividing these by their norms. So first one, so this vector becomes this, and the second, and again the order here is important, would be this should have been 2. I don't know why I was doing it that way. And this will be negative 1 over square root of 3, negative 1 over square root of 3, and then 1 over square root of 3. Okay, and then the third one is, you can see we have 4 plus 2 is 6. So negative 1 over square root of 6, 2 over square root of 6, and 1 over square root of 6. So now these three columns are going to form our vector V. Okay, and if we write it down, let me just write it in slightly neater way. So here we are. We have this vector normalized as the first column, and this one as the second column, and this one, turned into your unit vector is this column. And now what we have is this, that is, let's notice this here, that is, if we go ahead and bring our vector A back, all right, and we multiply A by this unit vector, unit eigenvector corresponding to 16, we are going to get 16. Or in other words, the norm of that, let me first write it down, that is the norm of this vector will be how much? That will simply be 4. All right, and as you can see right here, we have a square root of 16 as 4. So we will look at the eigenvectors corresponding to the, or the unit eigenvectors corresponding to the non-zero singular values. Okay, and that will go like this. Here we go, and if we multiply this here, then as you can see, we are getting our square root of 6 as the length of this vector. Okay, so if we, so you can see this here, that is the length of this vector, as you would expect, is 4. So we can create a unit vector here. One moment, right here, 2, 1. So if we divide this by 4, what we will get is that we will get 1 over square root of 2, and here we get the same vector, 1 over square root of 2, while in this case we will divide it by square root of 6, so we will get the same vectors. The only difference would be we will have a negative sign here. Okay, so what we have is we are going to write a factorization of the type U, and let's go strictly the way the book writes it. Like it writes the middle vector, the middle matrix as sigma, and that is we have V transpose here. So what we will have is our U will be the matrix with these two columns. Okay, so here we are. So this is our first column. All right, and then we have let me put the second column right here. So first vector is the same, and second one is the same with just negative sign here. So I will write negative. Okay, and in the middle what we will have is that we will have a vector of this size, and here I will write 4, the first singular value, and these and these columns are what? 0, 0, and here I have 0, and then I'll have square root of 6. All right, and then so this is in the main diagonal here, and then what we will do is that we shall write the transpose of this matrix at the end, and that will complete that factorization for us. So now let's just go ahead and write the transpose of this, and the transpose of this I'm just going to let it, let the computer do that, and it did that with like rationalizing the denominators, which is all right. So I did not complete the previous step, it's right here. And so let's see if our factorization is correct, or I have to go ahead and find my mistake. Let me just decrease the size here, and no, I made some mistake somewhere. Let me see. So let's see here. So we got this 2 by 3. Just looking at this, well, this is 6, so this is 6, 2 minus 6 is 1, okay, and then we got this whole thing will be 6 over 6, so then we have negative 1. Look like we are all right, because this would be 6 and this is 2, because so that is going to be 3, and I'm just being, so this is again 1 plus 2 is 3, and then 6 over 6 is 1. I mean, I'm doing the arithmetic and pass the eigenvalue calculations, but anyways, so let's see if this is the correct matrix. I think we got it right, or yes, we did. So the factorization, yeah, so the factorization worked here, and so this is just called singular value decomposition, and here we are using the singular values of this matrix A, and again the singular values are what? They are the square roots of the eigenvalues of A transpose times A. Okay, and there's a lot more to it, as you will read in the, as you have read or will read in the chapter. Okay, and yeah, let me know if you have any questions. All right. Or let me just do something else real quick. That is, you saw that we have this factorization, the singular value decomposition of this matrix here, and something, an exercise from before may come out of this decomposition as show and tell, even though the decomposition may take longer. So you know this, that if we can take this this matrix, or we can use this matrix to define a linear transformation from R3 to R2 in the following manner. Sorry, I don't know why am I rushing. Okay, so here we are just going to define a linear transformation T from R3 to R2, and what we are doing here is that we are taking our definition as that Tx is Ax. Okay, all right. So now say we would like to find a unit vector x such that this value, or the norm of Ax, or the image, is the maximum. In other words, or in other words, we would like to see that if we take this unit sphere with center at the origin in R3, okay, then what will be the maximum value, or rather at which point or points are the values attaining max for this domain. Okay, so notice this, that if we want to see where this norm of Ax is max, okay, then remember this, you did that a lot in calculus, like Ax is max means Ax square will be max, and you know this, that we can write the, when we are writing the square of norm, that is simply this transpose times the vector, right? Okay, and there we go. So we have x transpose, okay, then transpose of A, all right, and then Ax, all right. So this is what we get, and now this will be maximum when, if you recall, so when x, of course, the unit vector x corresponds to the largest eigenvalue of this symmetric matrix ATA, and you know that that largest eigenvalue is 16 in this case. So what will happen is that the max, and this will be the maximum value for this. So if we are looking at the maximum value for this quantity, so that will be square root of 16, that is 4, and it occurs at the point, let me first erase these. So it occurs where? At a unit vector corresponding to 16. All right, and what is that unit vector? Let's get that unit vector down here. Right. So that will be the column vector, this, because we had obtained this matrix as what? As a transpose of this matrix, right? So that's the column right here. So what we have is this here. If we take our original matrix and multiply that with this matrix here, that unit vector, then we should get 16 as we saw earlier, or a vector of like length 4, okay? All right, so you can see the length of this is 16, so the square root is 4, and that's the maximum distance from the origin. All right, so let me know if you have any questions, and it's just too late in the morning now to stretch any further. All right, so just look forward to your questions, okay?